Hello again, everyone, and welcome to another stream here on Freaky Physics. And we are going live with another lesson. And yep, still reviewing for IBDP physics, and we'll get to our lesson now. Okay, but first, let me connect the board. There we go. All right, let's get ready. Okay, let's join the lesson as well. Okay, let's enter the classroom real quick. Okay, let's see. Okay, haven't adjusted the settings yet. Let me adjust those. Just real quick. Huh? All right. A lot closer to my actual skin tone. In other words, I look more natural. There we go. Let's go to the map. Okay. Right, still nothing on the chat. Let's wait further. But I have been sent new problems to go through, so let's get those open and get going. Just 5 problems for today. 5 new problems. Let's get to some of the older problems from before. Okay. Solid weight. Okay, we have a few problems on gravity, um, electromagnetism, oscillations, okay. Okay. All right. We have some relativity problems, but mostly new stuff. This one's done. Uh, this one's not done yet. This one not done yet. There we go. Hello.
Hello.
Good day there, Dee. All right. How's everything today, Kita?
Great. How about you?
Doing good. You're feeling much better, I hope.
Yeah.
All right. Great then. Um. Okay. So let's see. How many problems you send over today? 1, 2, 3, 4. 1, 2, 3, 4, 5. All right. Um. Okay. Let's just go through the problems now. Let's start with the ones you sent today. Okay. For a
Okay.
change, we actually are all we're basically done with everything from last week, right? Okay. So let's.
Yeah, we had the relativity questions, but
Yeah.
we can come back to them.
We'll go back to that in a while. Okay. The reason for that, well, we want to get all the relativity questions today after we do these easier ones. Okay. All right.
Okay.
So, um, let's do that, and let's share my screen here. All right. There we go. Okay. So let's start with this. So you have this flexible solenoid shown here. Um, and you have to explain or state first and then explain what happens to the separation of the coils when the switch is closed. Okay. Um, before we go anywhere, one thing that would be really helpful here to remember is that conductors, or let's just say wires for now, okay? That wires that carrying, let's zoom in a bit, okay? wires carrying current in the same direction. So this is now a shortcut in case you want to remember it. Okay, in the same direction, uh, attract each other. Okay, magnetically. Let's put that word magnetically here. Okay, so with that in mind, magnetically. Okay, so with that in mind, I'm going to draw just a portion of the solenoid first. So I'm gonna draw just the upper portion of the solenoid and just two coils of the solenoid right there. Let's say that in this case, the current is flowing in the same direction. And we can easily say that the current is flowing in the same direction because of the way that the solenoid is set up. It's always, yeah, it's gonna carry current from the battery going left, then down, then through the coils like this.
Mm,
All right. So you can
okay.
easily see why at the top of the solenoid, those sections at the top of the solenoid, they are carrying current in the same direction. Okay. Now, because of this, because they are carrying current through them in the same direction, and we've just explained that they attract each other. So this coil here is gonna move that way. The force on this coil is gonna go that way, right? Similarly, the force on this coil is gonna go this way. Okay. So what? So if there's a gap between those coils, what happens?
It closes.
Okay. Now this is the short way, but because of the word "explain" in the problem, we have to go into the actual physics behind it. Okay. So,
Mhm.
so the shortcut tells us what happens, the state part. So coils come closer, right?
And if there was a coil in the middle of two, then it wouldn't move.
Um, if there were only three of them, yes. But basically, what's gonna happen is all these coils are gonna go that way, and all these coils are gonna go this way.
Oh, okay.
Okay. Now, it would still also kind of depend on which part of the solenoid you're kind of holding stationary. But if there's nothing holding it stationary, then it's definitely gonna go to the middle. Okay.
Okay.
So the coils come closer to each other. But let's go to the physics now, and to each other. Okay. Now, if we go to the physics, why is that the case? Remember what we were doing last week. I'm gonna do. You remember this problem where you have x, y, and z. You remember this problem, right?
Yeah.
Okay. This is gonna be similar to that. Now, I'm gonna show you how to do it, but for now, we're gonna erase z. We're just gonna look at x and y. All right. In this case, let's make the current flow in the same direction in both cases. So let's make it both go towards the page like this. Okay. So what we want to do is step 1 is to draw the magnetic field around X. Okay. And then step 2 here is to find the force on Y. That's all we're doing here. Okay. There's a different way of doing it, but I find that doing it like this is a lot easier to see what's happening. The other one, the more physically demanding one, it's really hard to see what's happening. So we won't go there. We'll use this one instead. Okay. So if we do this, if we look at the magnetic field around X, which way is it gonna go? Clockwise or counterclockwise? Going in the page. So right hand.
Counterclockwise.
Going into the page, use the right hand, right? So
Oh, wait.
we'll
Yeah.
use right hand
Yeah.
here.
Clockwise.
Okay, so this is right hand. And for the force, we're gonna use left hand. Okay. So this is going to be clockwise. So the magnetic field here is gonna go clockwise like that. Okay, but I'm not gonna draw the whole thing. I'm just gonna draw this part here. So the magnetic field due to X near Y is pointing downwards. Overall, it goes clockwise, but we're just going near Y. And near Y, it's pointing downwards, right? Now, let's take a look here at B and use the left-hand rule. According to the left-hand rule, this is now the magnetic field it's in. The current is going in, right? So
Yeah.
we do FBI. So I is going in. So into the page, magnetic field is down. So it points the force that it experiences is gonna point that way. All right. And then the third part, there's actually a third part here, is to write the force on X. And the third part is gonna be easy because what's the force on X? Force on X. That's gonna be equal to the force on Y, but negative. In other words, that's Newton's third law. Okay. So three things go into getting these directions. Magnetic field by X, then force due to the magnetic field, and then Newton's third law. Okay. All right. So we see now why these would attract each other. Okay. Now if you reverse the current in Y, but you don't reverse the direction of the magnetic field, which way is it gonna go? It's just going to go the other way. Okay.
The force, you mean?
Yeah, the force. So if you reverse the current, the force gets reversed. Okay.
Okay.
But if you reverse both currents, so that's another short way to do it. Okay. If you reverse one thing, whether it's the magnetic field or the force or the current, you reverse one of those things. Um, you reverse one thing but not the other, then you reverse the third. Okay. So one flipping changes the other thing. Double flipping changes nothing. Okay.
Okay.
All right. So with that, let's go to the final bit. Let's actually do the explanation here. So how will we write the explanation? We're just gonna say the magnetic field from X. Okay. Magnetic field. Let me zoom in a bit so we can write better. Okay. The magnetic field from X. From the top part, let's just say it like that. The top from one coil. Let's do it like that. One coil will exert a force on its neighboring coils, right? Neighboring coils. Exert a force on its neighboring coils. And let's put the word attractive. I'm gonna write attractive here, make it faster. Okay. Attractive force on its neighboring coils, compressing it. Okay. All right. Any questions here?
No, it's clear. Thank
All
you.
right, that's very clear. All right, great. So let's move on to the next question. This one's done. Okay, hold on. Which one is gonna be good? Okay. Um, that's not it. Does it have a second part? No. All right. Uh,
There's a second part to the one that we did yesterday, which is the one we have to draw a graph. And then there's second parts to this one.
Yeah. Hold on. Let's go to this bit, the graph. Okay. So now that we've established that's gonna happen, now we're gonna do another part. We now have a ring approaching the solenoid, right? Where does it say B though? I don't have the B. Okay.
All right, either way, let's just do this next bit. Okay, before we do the graph and everything, let's go back to the equation for, what's this, for the Faraday's law of electromagnetic induction. Okay, so remember that Faraday's law, the EMF, the induced EMF, that should be equal to the rate in change in magnetic flux over change in time, right? And there's a negative here. So this is the equation we want to work with in here. And even though we're not exactly using the equation, this should help us with the graph. Okay, so first of all, let's take a look here in the flux. Now, the ring, if this was really, really far, infinitely far from the solenoid, what would you expect the flux to be there? So remember, the flux here, a magnetic flux, basically you're just saying magnetic field lines, right? Okay. So when you're really, really far away from the magnet, what would you expect the magnetic field lines to be doing? How many field lines would be flowing through the ring or going into the ring? You'd expect it to be zero, yeah?
Yeah.
Okay, but here's the thing. So at the beginning, it's really far, so you expect it to be zero here. And, um, okay, and as you get closer and closer and closer to the solenoid, the magnetic flux becomes stronger and stronger and stronger. Okay. Um, does it be, is it gonna be exponentially? It's not gonna be exponential. It's gonna get to a certain limit here. So this is the maximum, right? Maximum flux. Okay. So basically, you could get something similar to um, a curve like that. It's not gonna be a straight one. Sorry, it's not gonna be like that because the further away you are, it's closer to zero. So it's gonna curve a little bit like this. Okay. There. Let's just redraw that. I think I'll zoom in again to make it easier to draw. Okay. So again, you would expect it to be close to zero at the beginning. Then it's gonna start increasing like so. A bad one. Let's just do it the other way. Something like that. Okay. Now.
And sorry.
Go ahead.
If the ring goes in and then goes out.
Okay. Does it go in? Oh, it can fit within the solenoid. So okay, let's add that. Okay, since it can go into the solenoid, so let's just draw the positions first. So this is gonna be the one end of the solenoid. That's gonna be the other end of the solenoid. Here on the inside, the magnetic flux is constant. Okay, so inside, uh, magnetic flux, or rather, magnetic flux is constant. Okay, so it's gonna be like this here. A horizontal straight line here, and then it's gonna curve up like so here. It's gonna curve down like so, like that. Okay.
Okay, and why does it curve? Why can't it go straight for the first and last part?
Well, let's think about it this way. Here, and then here, and then here. All of these, if these are still all relatively far from the solenoid, the flux here would still be approximately equal to zero. So that's why it curves here, because far away from the solenoid, you're still approximately zero. You get the idea? And then the only way this can curve further is it just gets stronger all of a sudden. The closer you are, though, it's much stronger. So in other words, the closer you are, the faster it changes. So that's why it's gonna have to curve like this. Okay.
Okay.
All right. Let's remove just this. Okay. Now, we're now going into the second part, wherein we need this equation. Now, I can change this because this kind of looks like some sort of, well, we're looking at the rate of change, right? So we can actually change this into a derivative. Now, why is this important? Because if you know how to work with derivatives, then all you have to really understand is this means this is the, either way, this is the gradient, right? gradient of phi versus t, right? Okay, so that's what you have to do now. And since what's happening, all right, so what's happening here? What's the gradient here at the beginning? 0, right? Okay, and then what's the gradient here? You see here that the gradient slowly changes, but it's increasing here all of a sudden, right? So what we're gonna do again is we're gonna do that, okay? And the EMF, it's just asking for the magnitude, so we will ignore the negative sign, okay? So here at the beginning, it's still gonna be like that, and here at the end, it's still gonna be like that, right? Then here, it suddenly changes right here, so it's got a big EMF here, okay? Here, basically the EMF here, if you're really gonna do this, it should still curve, or it could be a straight line, but if it curves, it's not gonna curve as much. It's gonna be like that. So less of a curve, more of a straight line, okay? But here though, what's the EMF here? Because it's not changing on the inside, it's gonna be 0 like that. Okay, again, no change in phi, right? So that's why it becomes 0 like that.
Okay.
Okay. Right. Okay. All clear here?
Yes.
All right. Good. Done. Okay. Let's do 2 more problems that are no. There are 2 more problems here before we get to relativity. Okay. Copy this image.
Yeah.
All right. So next problem. It's still part of the oscillations. Now the oscillations. Oh, okay. Sorry, this is the other one. This is a continuation of the speaker problem from before, right?
Yes.
Okay. So the oscillation of the speaker are very lightly damped, and then the support is made to oscillate with frequency f. Okay. Draw a graph to show that the variation of the driving frequency f of the amplitude a of the oscillations, and no numbers are required. Okay. If we go back to the problem though, where's that actual problem? Let's just, okay, hold on. I'll just get the actual problem first, just to make it easier. Copy this. Sorry. There we go. And just making sure. Okay, so to make sure, this is the continuation of this problem, right? Hold on. It's still loading. This problem, right?
Yes.
Okay. All right. So since that's a continuation there, let's close this now. The idea now is that this is oscillating. Okay. And this is oscillating, and then the oscillation itself is very lightly damped. In other words, when it oscillates, you barely see it becoming smaller, but it is gonna get smaller over time. Okay. So let's do this here. Lightly damped means oscillation will eventually stop, right? Eventually stop. Okay, but the thing is, it's given here that the support, what's the support? The support would be this. Okay, so this support, it's made to oscillate with the frequency f. In other words, if you think about this, this is the one that's vibrating with the frequency f. And then this is vibrating at some other frequency, oscillating at some other frequency, whatever. Okay, so we don't really care about the oscillation just yet. Okay, okay, but we do know that this thing was oscillating at. We got an answer earlier. What's the frequency of oscillation for this thing?
60 hertz.
60 hertz, right? So, oh yeah, okay, so that's gonna be 60 hertz. So that's gonna oscillate once a second. Okay. let's just make sure. I just want to make sure. But I think, yeah, it's 60 hertz. Yeah, we got it, 60 hertz. Okay. So the oscillation is 60 hertz. So, um, so what's the key idea here now? Since you have two frequencies, that means one of them is a natural frequency and one of them is a driving frequency. So which one's the driving frequency? It's this. This is the natural frequency. Okay. Now, what do we know about driving and natural frequencies? When the driving frequency is equal to the natural frequency, the amplitude of oscillation is gonna be maximum. Okay. All right. Um, okay. So what's gonna happen here? You're gonna get a maximum oscillation amplitude there. That's your max. Okay. Everything else will be smaller than that. Of course, when you get to zero, there won't be any oscillations, right? Okay. Um, what also happens if there is another thing here? Um, when the natural frequency and the driving frequency are multiples of each other. Okay. Um, what was the term here? Resonance. Okay. Um, okay. What else? Hold on. There's something I want to make sure that I'm saying right. I'll just check it out real quick. Okay. Now, this. Okay. So basically, what happens here is that when the frequency is matching there, the amplitude is going to be maximum, and then slowly but surely it's going to go to zero. It's not going to curve. So I'm just going to draw that here for the 60. It's not going to be a straight line like that. It's not going to be like that. Okay. What the curve? It's going to curve because still, when you have the frequency that's still close to that, you're still going to get some sort of maximum possible value, close to the maximum value, like that. Okay. Um. Okay, and we're gonna mark an A over 2 spot here. Okay. Okay. Now, the idea here is that when you get to this particular thing, this length should be equal to your angular frequency. So, in other words, this should be 220 pi. Okay. So, in other words, from 60 to here should be 60 pi, and then from here to here should be also 60 pi. Okay. So what does I don't think we're going to that level, to that deep of a level, but basically what you want to do is that it's gonna be 60 pi. It's gonna be around 360, right? So in other words, you're gonna get some sort of curve like this. Okay? And the curve is
Sorry.
it's gonna be like that.
Mm-hmm.
Go ahead, you have a question.
I don't understand why the angular frequency would be those two measurements.
Because the angular frequency is related to the what's this? Hold on, let me just double check whether if this is correct. The graph I'm looking at is correct. Small damping. Okay, sorry. I was looking at the wrong graph. We had angular frequency. This is only frequency, right? Um, basically, when you get to this, you should be very close. We should be very, very close to zero. So this and this. Okay. So this is 30, and then this is 90, right? So what you need to do here is that this needs to be somewhat like this already. And then the rest of this is just gonna taper out like that. Okay.
And what about the other oscillations? Like this is when it reaches this maximum.
Yeah. So what does this mean? So let's just go to what this curve actually means. So when your driving frequency is 60 hertz, that's what this is, right? then it matches the natural frequency here. You're gonna get maximum amplitude. Now, what if it was 61 hertz or 59 hertz? That's still pretty close, right? Still pretty close to the actual frequency. So we're gonna expect it to be a little bit lower, but not by much on that amplitude that it reaches, right? But once you get to half of 60, that's 30 hertz, right? You're gonna expect that you're gonna expect the damping to be really fighting against the oscillation of the driving frequency. So basically, the 60 and the 30 hertz here kind of are fighting each other, and therefore you get a smaller frequency here. Sorry, a smaller amplitude. Okay, and the more you go away from 60, the more it's gonna be the more that the driving frequency and the natural frequency don't match, and the smaller the amplitude will be. Okay,
So the driving frequency changes?
No, yes, in this case, sorry, yes, the driving frequency is changing. That's what it says here on this line here. Okay, now, I'm gonna erase this for now just to make it easier to see. But you do see here that it's kind of symmetric, right? So all we're gonna do is extend that symmetry here. But of course, because it's not gonna be totally symmetrical, because once you hit a zero frequency, it's not gonna oscillate anymore. So it's just gonna be there, right? Or it's just gonna have a really tiny oscillation. So it's gonna be similar. The closer you get to infinity here, the closer it's gonna get to zero. Okay.
Okay.
All right. For small damping, that's gonna be what it looks like. Now, what if it was medium damping? Medium damping would be a bit lower on the no, let's say that the amplitude's still the same, but it's gonna be wider. So the bigger the damping, the wider it gets. Okay. All right. All right. Any other questions?
No.
Okay.
Not for now.
So state and explain what happens now. So the driving frequency is set at the resonant or natural frequency. So the sensor records the range of frequencies found in C, and the driving frequency is now decreased. State what happens to the range of frequencies recorded by the sensor. Okay, so let's go back to this. This is now the sensor, and the sensor is now actually looking at the frequency of the sound that's being emitted, right? So this is a little bit tricky because we're now talking three frequencies: the natural frequency or the resonant frequency, and then we have the driving frequency, and then we have the frequency of the sound being produced.
Right.
And so three frequencies, three different things. In this case, the range of frequencies recorded by the sensor. Well, what happens when the driving frequency is the same as the natural frequency again? The amplitude is maximized, right?
Yeah.
Now, what happens when the amplitude is maximized? So, let's zoom in again so I can write better. So in this case, when FD, so let's just do it like this: when the driving frequency equals the resonant frequency or the natural frequency, the amplitude is bigger than the initial amplitude, where, let's just do it like this, where A0 is amplitude before when FD is 0, right? Amplitude is when FD equals 0, okay? So we'll just write this, okay? So what's happening here now, because there is no when FD, we have a much bigger amplitude compared to the normal or the initial amplitude. So and then the idea now is that when you increase the amplitude, you increase. So when amplitude is larger, Vmax is also larger, right? Because of the energy being stored in the oscillation. The bigger the amplitude, the more energy stored, right? And therefore, the faster the maximum speed. Now, because of this, Doppler effect is gonna have Doppler effect has is larger as well. Okay. In other words, what happens to this thing? The range of frequencies is now larger as well. Range of frequencies um, that that the sensor senses. Range of frequency on sensor is also larger. Okay, so that's what happens to the frequencies recorded by the sensor. Since the range of frequencies is now larger, then the maximum is larger and the minimum is smaller. Okay, that's what happens. We don't know the exact values because we don't know the exact value of the amplitude at the moment. Okay. All right.
Okay.
All right. Hope that makes sense. All right. Last question. That's not relativity. Is gravitational potential. Okay.
Okay. Wait. Sorry. Could
Go
I
ahead.
actually ask a question? So last time we calculated the frequency of the oscillation using the kinetic energy
That's
and
right.
the velocity,
That's right.
which only happens like when it's off the equilibrium and on both sides.
That's right.
So the frequency increases if there's more kinetic energy, but there's still going to be two frequencies.
Yeah, there's still going to be a maximum and a minimum frequency again because of Doppler effect. Because what's happening in the oscillation, there's going to be a time wherein the speaker is coming closer to the sensor, and in those cases the frequency observed is bigger. And then there's going to be a time wherein the speaker is moving away from the it's moving away from the sensor, and that decreases the perceived frequency. But because it's moving faster now, it's going to both increase that maximum frequency and decrease that minimum frequency.
But the observed is always going to be 2.
Yeah, there will I wouldn't say there are two values, but there's a range of values between those two. So let's say that one frequency, let's say, is just for argument's sake, let's say that it's 300 hertz, and then one of the maximum frequency is 400 hertz. Those are the two. Let's say those are the two values you get, right? Then that means you will observe every possible frequency between 300 and 400 hertz. Okay. Now, when you put the driving frequency in, what could happen is that the 300 hertz becomes 280 hertz, and then that 400 hertz becomes like 420 hertz. So it changes the ends, but it still covers the whole range. It's gonna be between those two values. Okay.
Okay.
All right. So in terms of numbers, all right. Let's go to this next problem here. The gravitational potential at the surface of a planet for radius r is v0. Determine in terms of v0 the work that must be done for a probe of mass m to bring it to the surface to a point at height r from the surface. Okay. Okay. It's easiest to do it like this. We do have an equation for the potential, right? Remember, I'll just do v instead of v0 for now. The potential, and let's put gravitational. Actually, since we're talking gravity only, let's just keep it at v here. Yeah, it's gonna be negative g, then the mass of the planet over the distance. And in this case, the distance I'll use small r for now, so we don't confuse it with the big R here. Okay. Now, it is going to be defined here that at r, radius r, on the surface, it's v0. So the first thing we're going to do is v0 is going to be negative g times the mass of the planet over r, big R, by definition here. That's what it's done for, okay? Now, when you go a certain height from the planet, so let's draw the planet here. That's going to be our R, and then that's going to be, this is just the height, h, from the surface, right? But the height here is also going to be r. So what's our actual distance that we need to do? So the distance that we need to do for the second part is twice the radius. So let's call it V1. Okay, it's gonna be equal to negative GM over 2R. Okay, so um okay, so what's gonna be the difference in potential? Change in that would be equal to negative GM times 1 over 2R minus 1 over R. And that's just going to give us GM over R, right? So that's a change in the potential. Now, what's the work done? The last bit here is easy because the work done will be equal to V times R. Small r in this case. Okay? Or better yet, delta R. Okay? So how much did it move? So that's going to be basically sorry, not that's not right. That's not R, that's M. Okay? Hold on. Work done is equal to M. Okay? Okay, because let's just do it like this. I think it's easier to see it like this. So remember, in terms of the gravitational energy, Eg, okay, that's going to be equal to um, V times M. Okay? Yeah, that's gonna be a bit easier. So we're gonna do E0 and E1, right? So that's just gonna be negative G. Okay, let's not do it like that. Let's do it like this. What's gonna be E1 minus E0? Easier. E0. That's gonna be our work done, and that's gonna be V1M minus V0M, right? But if we factor out the M, it's gonna be M times delta V, all right? And we do have an expression for delta V already. So that's going to be just equal to G big M small m over R. So the work done is equal to that. And that is done. What is our R here? Big R. Okay. All right.
Okay.
Questions done. All right.
Yeah.
Okay. All right. Let's do the relativity questions, but this time let's do the ones with calculations first. Okay. Which one has calculations? Okay, let's do this one. Okay. All right. We're doing which one here? C or D or both, or maybe all.
All.
All of them. Okay, let's do these now. Before we do this, when it comes to calculation, can I show you a quick trick? Okay.
Yeah.
So the trick here, whenever we're doing relativity and we're doing calculations, is you're gonna have to look at both reference frames. So trick. Draw both reference frames. Okay. This is gonna make it easier to see what's happening. So let's do it. Let's do it for D. Okay. So you have our. Oh, hold on. Let's not do D yet. Let's do C. Okay. Let's do C. So in C you have a rocket. Okay. So what is gonna be the thing? So we're gonna do the two things. So this is from the point of view of the rocket. So from Earth first. Okay. So according to the Earth, that's us. It's stationary. The rocket is moving past the Earth. So I'm just gonna draw the rocket like so, moving that way, right? With a velocity 0.6 c. Okay. And now we're gonna look at the second rocket. So let's label this rocket X and let's label this other rocket Y. This other rocket, according to the problem, is moving at the speed of negative 0.8 c. So it's gonna move this way, right? Negative 0.80 c, right? So the rocket's like that. Let's put the flame. Okay. Now The trick here now is we're going to look at the second reference frame. According to our problem in the second reference frame, determine the velocity of y relative to x. So we're going to look at x, rocket x. Okay? So in rocket x's point of view, it's not moving. So x is like that, right? And which way is the Earth moving? The Earth is moving at this speed 0.6, negative 0.6 c. Okay, that's the Earth, and that's the Earth. Now, and here's the thing: the third object, in this case, our rocket Y, is also going to be moving in whatever direction, but we don't know its velocity. Okay, so this is going to be v prime. Are we going to say v prime? Yeah, we're going to say v prime. Okay, so you see what's happening here. These two are our reference frames, and we just basically reverse the velocities for those. The other thing, the third object will have a different value for velocity. That's a trick. Okay.
But it will still be moving to the left.
It should be. If everything makes sense, it should be moving to the left, right? In fact, if we do this with Galilean relativity, it's still going to move to the left, definitely. But the speed will be, so in Galilean, how fast is y moving? In Galilean, you just take the difference in speeds, right?
0.2?
No. In this case, we're looking here, the difference in these two speeds, according to Earth. So that's going to be 1.2. 1.2 c. Okay?
Oh, okay.
Right? Okay. So it kind of makes sense in this case because remember, rocket X is moving away from rocket Y. And then for Galilean relativity, you just subtract the relative velocities of the reference frames. And that's, you subtract the velocities, and that's how you get the relative velocity. And we do know in relativity that this is impossible. This is faster than light speed, right? So how about Einstein? How about relativistic? Relativistic. How do we do it? We use the Lorentz factor in this case. Yeah. What's the equation that we can use here? Hold on. I'll just double check that I am looking at the correct equation. Can check the data booklet here. Okay, relativistic facts. That's gonna be still in A. Okay. V. Where's the V? U prime. Okay. In this case, we will change this to U. Okay. We will label this to U as well. So U is there, and this is gonna be U prime, right? So if we look into the formula in here, we have a formula we can use straight away. And we just put our values in. The formula, I'll just paste it here, is this. Okay, there. Okay, so in this case, let's actually use the values given to us. Our U is negative 0.8 C. And then our V is negative minus 0.60 C. Okay, that's just because it's still positive, but you have a negative here, a minus sign there, right? So, and then in this case, let's do 1 minus what's U? Negative 0.8 C times 0.6 C all over C squared. So the C squared here cancels out. Let's just put that in the calculator now. That's going to give us negative 1.2 C, right? But we're going to divide that by 1 minus, what's 0.8 times 0.6? What's 8 times 6? 48. 0.48. Okay. Did we do that right? That doesn't... Oh, sorry. There's a plus here. That becomes plus because of the negative here and the negative there, right? Okay. So with that, what's that gonna be? That's 1.2 divided by 1.2c divided by 1.48. That's going to give us 0.81c. Negative
Um,
0.81c.
but isn't the top number 1.4?
Oh, right. You're right. It should be 1.4. You're right. So let's do 1.4 instead of 1.2. 1.4 divided by 1.48. Right? That's going to give you 94.6% the speed of light, or 0.95c. Yeah? There.
Okay.
All right. So, okay. I think in these cases where it's pretty straightforward, you just draw the diagrams. You just make sure you label them properly accordingly. Okay. All right.
Yeah.
All right. Let's do one more here. Okay. Let's do D. Okay. This time, so we're looking at the time that the rocket and space station meet according to both clocks. Wherein you're given that the rocket leaves Earth with 0.8 c, and the distance is 16 light years. Okay. All right. So let's do that. Okay. But again, we'll do that trick wherein you separate the reference frames. This is from the Earth. Okay. Hold on. Which one is it? Yeah, Earth and rocket. Okay. So we're gonna do Earth, and we have rocket. So let's do that thing again, wherein we separate the um we separate the 2 points of view. So this is Earth, and this is the rocket going this way. It's gonna be 0.8 c, right? Moving that way. Okay, the space station is here, and we know that the distance from here to here would be 1.6 light years. That should make it easier to calculate for the first one, right? So 0.8c, 16 light years. Not 1.6, 16 light years. Okay? Now, what is going to change here on the rocket's point of view? What's going to change here? In this case, you can say that u equals 0. It's stationary, right? We're just gonna do that. V equals that. Now, what's gonna happen from the from the rocket's point of view, from the reference frame of the rocket? So that's the rocket. It's what's happening to it is the Earth is receding at that speed, right? Okay, it's receding at that point, but also at the same time, the space station is also approaching it at that speed. Okay, where u equals v. Okay, so it's gonna do just like that. Okay, so now the problem is, let's go back to the problem. Go back here. Time. Calculate the time that the rocket will get to the space station. So let's do it from the Earth's point of view first. So here's the thing about this. We don't know this actual distance yet. This is gonna be L prime, according to the rocket. Okay? So in other words, we need to know what that L prime is. But you know that's gonna be shorter than 16 light years because of light contraction. Okay? Light contraction. So what exactly do we need here? We need these two equations here. We may need both, but we're most likely gonna need just one. Actually, sorry, I think we're gonna need both here. Okay. So first of all, what's t? T here would be very straightforward. It would be 16 light years times 0.8 c. That's gonna give us how many? The time here would be the distance over the speed, light years over 0.8 c, and the light and the c cancels out, right? So that's going to give us 16 over 0 0.8. That's going to give us 106. Let's just do calculator. 16 divided by 0.8 gives you 20 years. Yeah. Okay, so that's the time it takes according to Earth. It takes 20 years to travel from Earth to the space station. Okay, now what do we do here on the rocket's point of view? In order for us to find the time it takes to travel that, we need to find L prime. In other words, we are going to use this formula right here. Okay, so in this case, our L is going to be our L prime, our X primes are L prime, our gamma is going to be, I'll just do it straight here, square root of 1 minus V is 0.8 C squared over C squared, right? And then this is going to be 16 light years minus 0.8 C times T. Okay, T. Is that right? Not quite. There should be T prime. Okay. Hold on. Let me just double check. Okay, we also need to know what T prime here is. So yeah, this length will be equal to C over CT prime. Okay. In fact, okay, sorry. This is gonna be easier. We need to find the T prime first. That's gonna be better. We find the T prime first, and then we just use L. Okay. In this case, what's T prime? T prime would be equal to, we do the 1 over square root of 1 over 0.8 C squared over C squared. Okay, and then we're gonna do T 20 years minus C squared. Our V is what? Our V is 0.8 C, and then our T was 20 years, right? Sorry, our
But
X
there's
is
no
16 light years. Sorry, 16 light years. Okay. So what happens? The
okay.
C and the C and the light in light years cancel out. So yeah, we solve that now. That's going to give us 20 minus hold on. Is this right? T equals 20 years minus 0.8 times 16 this time, right? So 16 times 0.8, it's gonna be 12.8. Okay, then the C squared cancels out. We're left with that. Then we do the gamma. 1 minus 0.64. That's going to give us 7.2 divided by 0.36 square root. Okay, we just put that in the calculator straight. That's going to give us 7.2 divided by 0.6, right? 0.36
12.
square root 0.6, that gives us 12. So this gives us 12 years. So the rocket, according to its reference frame, T prime is equal to 12 years. It's going to travel 12 years according to its reference frame. Then we're going to use this T prime to simplify the L prime. So finally, L prime is just going to be equal to the speed T prime. Okay? That's going to be 0.8 C times 12 years. Okay?
Yeah.
Okay. L prime. And of course, CY, that's just light years. So 12 times 0.8, what's that? Times 0.8, that's going to give us 9.6. 9.6 light years. Okay? So Okay, since we're just looking for the time, we just actually had to stop at 12 years. But I just wanted to calculate to L prime to see what's happening. The length contracted, but the time that it takes for the rocket is also gonna get shorter because of the length being contracted. Okay.
Yeah.
All right. Um. Okay. Any questions here?
No, it's actually I understood everything.
All right. So I hope this trick of putting the two diagrams together makes it easier to analyze. Yeah.
Yeah,
All right.
definitely.
All right. Okay. So that's done. Anything else you'd like to ask? We didn't get to the problems from last time. I think we'll go through them
Yeah.
tomorrow first. Then. Okay.
Okay.
All right.
Okay. Perfect.
All right. All right. So I'll see you. Yeah, tomorrow same time, and you have a good evening or a good day, and I'll
Okay.
see you then.
Okay. Thank you.
All right.
Have a
Bye
good
bye now.
day. Bye bye.
All right then. So that's the end of that. This, hello. Okay. Um, this person will be blocked for that comment. Okay, so Mr. Someone Anonymous, just say hello. Hey, who's watching? Let's see. Somebody's watching on YouTube. Hello, you still there? Yeah, I hope you found this useful with the review. Okay. Anyway, that's the end of the lesson today. So hopefully for those who were listening in or still there, you did learn something. Okay. So tomorrow we'll be doing more relativity problems. And the thing is, for me, and I've said this last time, um, I'm relearning it. I've learned it before, but I'm relearning it simply because I haven't actually taught relativity very recently until this year. So I'm kind of relearning it. But, relearning is a bit easier compared to learning from scratch. So should be up to speed in the next few lessons to help with that. Okay. But either way, technique I just showed you using diagrams to help you determine which one is which. It's gonna make solving, just if you're just doing straight solving, a lot easier. Okay, so with that, we'll end today's stream. But before we do, don't forget to like, share, and subscribe to the channel. We are on YouTube, Facebook, and we are all, I think we're already quite consistent in posting in Instagram whenever we go live. So notifications go on Instagram and TikTok. And when we go live, we're also on Twitch. So, okay, again, like I said earlier, I hope you've learned something today, and we're ending here today. So, wherever you are in the world, I hope you have a good morning, good day, good afternoon, good evening, or good night, and stay freaky, everybody. Bye bye now.